My name is Aditya Prasarasmani, studying in Sri Venkateswara College of Engineering, Bangalore. Today I am going to explain about antenna propagation using integral calculus.
Now let us discuss about antenna propagation using integral calculus. Introduction. This presentation explores optimizing antenna propagation through the application of integral calculus. We will dwell into the fundamental concepts and practical applications in the field of antenna design and optimization. Antenna. An antenna is a specialized transducer that converts electric current into electromagnetic wave or vice versa. Types of antennas. Isotropic antenna. It radiates power equally in all directions. Dipole antenna. It has two types. Half wave dipole antenna, quarter wave vertical antenna. The other one is parabolic reflective antenna, used for terrestrial, microwave and satellite applications. Larger the diameter, the more tightly directional is the beam. About antenna and propagation. In transmission, a radio transmitter supplies an electric current oscillating at a radio frequency, that is, high frequency alternating current, to the antenna terminals, and the antenna radiates the energy from current as electric wave. Fundamental of antenna propagation. Understanding the radiation pattern and propagation characteristics is crucial in optimizing antenna performance. Mathematical modeling of antenna propagation. Applying integral calculus to the model of electromagnetic field around an antenna enables precise analysis of propagation. We will explore the mathematical principle behind the modeling approach. Antenna gain. Antenna gain is a power output in a particular direction compared to that produced in any direction by a perfect omnidirectional antenna. Optimizing antenna gain. Using integral calculus to optimize antenna gain involves maximizing the power radiated in a specific direction. We will discuss the mathematical techniques and practical considerations for achieving this optimization.
Optimization. Applying integral calculus to optimize antenna arrays involves analyzing the combined radiation patterns of multiple antennas. We will explore the mathematical methods for achieving optimal array performance. Real-world applications of integral calculus in antenna propagation optimization extend to the fields such as wireless communication, radar systems, and satellite communication. We will explore these applications in details. Challenges and limitations. While integral calculus offers powerful tools for antenna propagation optimization, there are challenges such as complexity and computational resources. We will discuss these challenges and potential solutions. Emerging technologies such as machine learning and smart materials are poised to revolutionize antenna propagation optimization. We will explore the potential impact of the inventions on the field. Case studies in antenna propagation and optimization. We will examine real-world case studies showcasing the successful application of integral calculus in optimizing antenna propagation for diverse applications including 5G network and IoT systems. Key takeaways. This presentation has provided a comprehensive overview of the integral calculus and how leverage to optimize antenna propagation. We have explored the fundamental concept, practical application, and further trends in the field. Now let us discuss about the application of antenna. Antennas are devices that are used to transmit and receive electromagnetic waves. They are used in wide range of applications including telecommunications, wireless communications, navigation, broadcasting, and military. Telecommunication. Antennas are used in telecommunications systems such as cell phones, radios, and television broadcast to transmit and receive signals. Wireless communication. Antennas are used in wireless communications systems such as Wi-Fi, Bluetooth, and cellular networks to transmit and receive the signals over a short and long distance. Navigation. Antennas are used in navigation systems such as GPS and radar to determine the location and the speed of the vehicle and aircraft. Broadcasting. Antennas are used in broadcasting systems such as television and radio to transmit a signal over long distance to be received by the viewers and listeners. Military. Antennas are used in a military system such as radar and communication system to detect and track the aircraft and ship and to communicate with the troops on the ground. Wave propagation. The process by which electromagnetic wave move over space is referred to the wave propagation. Line of sight waves and non-line of sight waves are the two primary categories that these waves fall under. Line of sight wave propagation occurs when electromagnetic waves travel in a straight line from a transmitter to the receiver without being obstructed by any objects. Broadcasting on television and radio are examples of point-to-point communications that frequently employ this kind of propagation. Now we will discuss effects of wave propagation. Effects of wave propagation are diffraction, polarization, multipath fading, attenuation, barriers, absorption, and damping. Environmental factors and optimization. Environmental factors such as abstraction and atmospheric conditions can significantly impact antenna propagation. We will examine how integral calculus can be used to optimize antenna performance in varying environments. Ferry's free space radio circuit formula PR by PT equal to AR into AT by D square lambda square, where PT is the power fed into the transmitting antenna input terminals. PR is the power available at receiving antenna output terminals. AR is the effective aperture area of receiving antenna. AT is the effective aperture area of a transmitting antenna. D is the distance between antennas. Lambda is the wavelength of the radio frequency. And PT and PR are in the same unit of power. AR, AT, D square and lambda square are in the same units. Contemporary formula PR by PT equal to GT into GR to lambda by 4 pi D whole square, where GT and GR are the antenna gains with respect to an isotropic radiator of the transmitting and receiving antennas respectively, where lambda is the wavelength representing the effective aperture area of the receiving antenna and d is the distance separating the antennas. To use the equation as written, the antenna gain are unitless values and the unit of the wavelength lambda and the distance d must be the same. Conclusion. In conclusion, the integration of integral calculus in antenna propagation optimization offers unparalleled potential for advancing wireless communication and telecommunication technologies. The insights gained from the presentation will propel further inventions in the field.